Now let's observe something about this y equals x squared function. We've already seen that the graph is symmetric with respect to the y-axis. The y-axis forms kind of a reflector so that what we have on this side is a mirror image of what we have on this side. What we have on one side is a mirror image of what's on the other. This is related to the fact that we observed when we evaluated the y equals x squared for the various values of x, that the value that we get for x equals 2 is the same as the value we get for x equals negative 2. And the same is true for x equals 1 and x equals negative 1. The two values of y, the two values of our function, the two y values, are equal. And for 1/2 and negative 1/2, the same is true. So it appears that negative x, in general, gives you the same value as x. So we can write a little note here that negative x and x yield the same y value. And let's make sure that the camera is high enough to read that. Okay, so x and negative x give you the same y value here. Okay, over here we have y equals x cubed, and that's not quite true. Now the values that you get for x and negative x are related, but the value for negative x is the negative of the value that you get for x. Okay, so x and negative x are going to give you y values of opposite signs, same magnitude, opposite signs. So I'm going to write down a little note there. I'm not going to do it on camera in the interest of your time. Now I don't have a lot of room up here. I didn't anticipate writing this, but the statement is that x and negative x yield equal and opposite y values. So there's our statement, equal and opposite y values. So we have two different behaviors here, and of course we see how that works with the graph. If you look at the orange graph here, the graph here is of the same shape as the graph here, but it has to be turned around. Now there's another way of saying that. We say that the graph is symmetric with respect to the origin, and we've already seen what that means in other examples. Now neither of these is true here. 2 and negative 2 don't give you equal values. They don't give you equal and opposite values. Okay, but what about y equals x minus 1 squared? Well, there is kind of a symmetry around 0. We get 1 here, we get 1 here. If we went out to x equals 3, we would get 4, which would match the 4 that we get here. We'll explore the symmetry here, but it definitely does. You definitely do not have symmetry with respect to the y-axis. The value you get for 2 is 1. The value you get for negative 2 is 9. They're certainly not equal, nor are they equal and opposite. Now for the other two graphs, y equals 2x squared, what do we have? Well, x equals 2 gives us this, x equals negative 2 gives us this. They're equal. And these are equal, and these are equal. So we again have the behavior that we had for y equals x squared. And it's not too surprising that that should be the case, because the values we have here are double the values that we had here. So that if these values are equal for x and negative x, when they're doubled, they're also going to be equal for x and negative x. Okay, and then y equals x squared plus 2. Well, it turns out we have exactly the same behavior for x equals 2 and negative 2. We have 6 and 6. Again, and same for the 1. We get 3 and negative 3. That's for 1 and negative 1. For 1/2 and negative 1/2, 2 1/4 and 2 1/4. Again, that shouldn't be a surprise. If we add 2 to these values, they're going to maintain the same symmetry. If this is equal to this, then when 2 is added, the results are going to be equal. If these two are equal, if you add 2, that result is going to be equal. So writing out pretty much the same thing, but using the notation y equals f of x instead of just y equals x squared, for example. if x and negative x yield the same y values, as is the case for y equals x squared, x and negative x give you the same y values, then the graph is going to be symmetric about the y-axis. And we can embody that condition with a test that says that f of x is equal to f of negative x. Now, how does that f of x notation come in? Well, f of x is what you evaluate to get a y value. F of x is the y value corresponding to x. What's f of negative x? It's the y value that corresponds to negative x. This says that the y value corresponding to x is equal to the y value corresponding to negative x. That's exactly what we were talking about here. Okay, now, if x and negative x yield equal and opposite values, then the graph is symmetric with respect to the origin. And we've drawn that out. We'll probably draw it out again here in a little while. And the test for that is that f of x is the negative of f of negative x, meaning that the y value you get for x is equal and opposite to the y value you get for negative x. And that's the case with the y equals x cubed graph. Now we apply this test, and we could also apply this test to f of x equals x squared plus x cubed. How do we apply the test? We evaluate f of x, we evaluate f of negative x. Now we don't get to pick our x value, we just do the expression for f of x, which we already have, and for f of negative x. Okay? If f of x equals x squared plus x cubed, then what is f of negative x? Well, we've replaced x by negative x. So we replace the x's in both of these terms by negative x. We get the quantity negative x squared and the quantity negative x cubed. When we square negative x, we get x squared. When we cube negative x, we get negative x cubed. Now, we can see very clearly that f of negative x matches f of x on the x squared term, so that term's fine, but the x cubed term has opposite sign here. And that means that the test for symmetry does not hold. The test for symmetry about the y-axis, which is f of x equals f of negative x, does not hold. It's false. F of x is not equal to f of negative x. We conclude that there's no y-axis symmetry. And then negative f of x. We want to check and see if negative f of negative x is equal to f of x. Well, negative f of negative x was seen to be x squared minus x cubed, so the negative of that would be negative x squared plus x cubed, and that's not equal to f of x either. So both of our symmetry tests, symmetry with respect to the y-axis, symmetry with respect to the origin, fail. And of course, here's a depiction of the graph of that function, and it's very clear that it doesn't have either of those types of symmetry. Now we apply the same tests to a couple of other functions. Let's apply the same tests to the function x minus 1 squared. Okay, now f of x is x minus 1 squared, and of course we can square that. We get x squared minus 2x plus 1. F of negative x is what? Well, we've replaced x by negative x, so we replace x by negative x. We get negative x minus 1 quantity squared, and we expand that square, and we get x squared plus 2x plus 1. Well, we see that these two expressions agree except for the 2x, which is negative in the first expression, positive in the second. These are different, so there is no symmetry with respect to the y-axis. And negative f of negative x isn't equal to f of x either, because, of course, negative f of negative x is the negative of this, which would be negative x squared minus 2x minus 1, and that's certainly not equal to x squared minus 2x plus 1. So f of x is negative f of negative x is also not equal to f of x. Our symmetry test again fails. Okay, let's try f of x equals 2x squared. Okay, what's f of negative x? Well, we replace x by negative x here, so we replace it here. It's 2 times the square of negative x. And if you square negative x, you just get x squared. So that f of negative x equals 2x squared, and that is equal to f of x. So f of x is equal to f of negative x. Therefore, we have symmetry with respect to the y-axis. And of course, our graph of 2x squared, the red graph in this picture, and it's kind of light. I've covered the other picture so we can see everything that's on this board, but right there is the graph on this series of graphs, and we can see that symmetry in our graph. Okay, we also test for symmetry with respect to the origin, but that's not going to happen. Got a little smudge there. Okay. Negative f of negative x, well, f of negative x is 2x squared, negative f of negative x is negative 2x squared, and that's not equal to f of x. So we do not have symmetry with respect to the origin. And of course, that's obvious from looking at the graph.